This is lecture 9.1 of Architecture 2351, Technology 1. It's covering the fundamentals of steel, presented by Glenn Hill, and based on the fundamentals of building construction, materials, and methods, 6th edition by Edward Allen and Joseph Iano. These series of lectures are going to be focused on steel frame construction. But first we're going to talk about steel itself. It's derived from cast iron. Cast iron preceded, of course, steel, and was used to initially formed to use as swords. And it contains about 2 to 4% of carbon. Okay, and you'll see where this is important. But in the 1850s, steel began to be able to be made in large batches, and a process called the Bessemer process was created, which allowed industry to begin to mass produce steel. It was what was called, then later, about 10 years later or 15 years later, the Bessemer process was improved by what is called the open hearth method, and began to develop steel, what we call steel as we know it today. Basically, steel is cast iron, which has reduction in carbon to 0.3% carbon, and the impurities that you find in cast iron, such as phosphorus, sulfur, and nitrogen, have been taken out, which makes the cast iron stronger and less brittle. And then to make steel, we added in manganese and silicone, and those two things gave the steel or the cast iron more strength and flexibility, and therefore we get steel. There are two methods to producing steel. One is called hot rolled, and the other one is called cold rolled steel. The first process we're going to talk about is what we call hot rolled steel. And as we talked about it, it starts with iron ore, and then a result is turns into steel. It's smelted where the cast iron is created. In other words, you take iron ore and you alternate layers of iron ore and a carbon-only coal called coke, and then you blast it with air to help force out the impurities, and of course you produce a lot of carbon monoxide. This is the one downside of making steel, is the production of carbon monoxide, and of course we've put scrubbers now on our steel mills to keep the carbon monoxide from going into the atmosphere. And then what is drawn off is what we call cast iron. Then this cast iron is converted into carbon steel. And so you take the cast iron, you oxygenate it some more with an additional furnace, either a blast furnace or maybe an electrical arc furnace, and then you add manganese, molybdenum, manganese for abrasion, molybdenum for strength, and vanadium for strength. And then if you're trying to create stainless steel, you might even add nickel and chromium for corrosion or to prevent corrosion. So those are just some of the additives that are added to modern day steel. There are a variety of others to produce other alloys, what we call an alloy. When we add to cast iron different materials, we are creating what is an alloy of carbon steel. Recycled steel, steel that's already been made, is often smelted rather than in a blast furnace in a electric arc furnace, because it doesn't have to get as hot to burn off impurities as a blast furnace does. And also it's a little bit more fuel efficient if you have access to for instance, hydroelectric power. Then once that steel is in a molted form, it is poured or shaped into what we call beam blanks or blooms. Okay, and then those blanks are then shaped by a process called hot roll steeling. This image here is just to give you a general understanding of the kind of the whole process. We start with iron ore. That iron ore has to be broken up into pellets, or what was called sinter, which is a smaller element rather than just pellets. That's then added with limestone, which is run through a crusher and made smaller. And then coal, which is run through a coke oven. And coal has a lot of impurities in it. And what you don't want to add to the steel. So what they do is they run it through this coke oven, and that produces a pure carbon. So the coal that comes out of this is called coke because it doesn't have any of the impurities that normal coal has in it. It's just pure carbon, which will get hotter and create a more pure fire. And then those three things are mixed together into a blast furnace. And this is where we begin to make cast iron. So that blast furnace creates molten iron out of it. And that molten iron then is sent to different furnaces depending on what it is they're trying to make. As you can see right here, scrap iron, in other words, recycled iron or recycled steel, is run through an electric furnace. It may also be run through an open hearth furnace, but not usually. And then, or it may be run through a basic oxygen. So that molten steel is mixed, is processed and mixed with existing iron ore. And so we have molten steel now. So we come out of the blast furnace with molten iron and add it with maybe recycled steel, or we turn it into steel through basic oxygen furnace or an open hearth furnace. Open hearth furnaces are not used as much anymore because it's not as efficient as a basic oxygen furnace. So the molten steel then comes down and to a continuous casting. This is made into blooms. So it's the molten steel is continuously cast and it is made into blooms or ingots of steel, if you want to think of it in that way. The other way is that the ingots, it's called ingot timming, and it's sent through a blending mill. So it may do one of these two things, but the result is that it gets into these ingots of steel called blooms. And then those steels, by the time it gets through here, they've cooled to a certain degree, so they're not as easy to shape. And so those ingots are reheated. And when they're reheated, then they're run through a process where the shaping of the steel starts being created. Okay. And so it can run through different processes. These are kind of two different processes to create a wide flange steel and then a standard steel here. But the result as it comes out here then is a beam or the shape we want, a joist, whatever that shape is being rolled through this process here. And then it's cut into lengths and shipped, and then packaged and shipped out to another person in the process who's a fabricator. And so the fabricator gets this kind of raw pieces, and then they will cut the steel again and shape it and put holes in it and do whatever it needs to be done to be turned into building materials. But basically what comes out right here, okay, in this cooling bed, set in this cooling bed is this right here, okay, some kind of shaped steel that's been rolled into a shape, and then the only fabrication they do is cutting it into small enough pieces so that it can be shipped easier. One thing you need to be aware of that in steel, most all the steel that we use is usually some form of a steel alloy. Okay? And there is an organization called the American Society of Testing and Materials, uh, called ASTM, by the acronym ASTM, and they set the standards for different types of steel. And some of those different types of steel are, mild structural steel. ASTM A36 is a very common alloy. Then they set the standards also for recycle, and done in mini mills. And when they do it in mini mills, it's usually recycled steel is less expensive and it's of a higher strength because it's gone through really a second process of removing impurities. Uh, and then it's a low alloy steel normally. In other words, it doesn't have a lot of extra additives to it. And then there's for wide flange, which is this beam right here, or girder right there, is a wide flange. And they set the standard for that, which is ASTM A992. ASTM A572 is for very high strength steel used in conditions like bridges and stuff like that, where you may have a lot of dynamic load to it. The thing you need to know is just that there's different steels that are made by adding different, levels of magnesium, uh, phosphorus and other things, uh, and that those standards are set by the American Society of Testing Materials. The engineer will normally be the one who specifies what. You're not, as an architect, going to be specifying which alloy to use. That's going to be done by your engineer as they design the steel structure. Steel is created in standard shapes and standard sizes. You usually don't custom make a steel. It's made around these standard shapes and sizes. In hot rolled steel, these are the major standards and standard sizes. We have an American standard beam, okay? And you'll notice one of the things, this is called a wide flange beam. And you'll notice here in this diagram, it's showing you that a 10-inch beam may have different weights, okay? This number here implies a weight. So the smaller web here, okay, this is called the web, this is called the flange. Okay? And you can see the difference, the range, and even the height of a 10-inch beam. And of course, the more steel that's in the beam, the stronger it's going to be. In a wide flange beam, you can see that the flange is wider, as you can see right here. And it has a whole range of different weights, and which just add more steel, even though the depth is the same. And you can see it here. This is a W10 at 33 up to 112. And what that means is the weight per foot, per linear foot of the beam. Then the other common, so we have wide flange and American standard beams. Then we have what's called a channel, which is a C shape, sometimes referred to as a C channel. And once again, standard depths, and then different thicknesses based on the amount of steel that's in, of course, which give it a different strength. And then we have an unequal angle leg and L shape or angle. This happens to be an unequal, and then you can see over here is the equal legs. And then what is called a structural T, okay, which is basically a T shape, usually used as intermediary supports or brackets. And then we have the bars, which we have, square bar, which may be different sizes, round bar. This is what is converted into this round bar. is what's fabricated into rebar, what we call rebar. And then we have just another bar that's unequal in size. So we have a square and then an unequal shaped or rectangular shape. And then also steel may be sent out as a plate, but it's called a plate. Here's a table of those different sizes and different shapes. And to be able to understand what a wide flange is, it's described, its example designation is a W. There's a capital W followed by the depth of the beam. So that's 21 inches in depth. And then there's an X. And then 83 inches, I'm sorry, 83 pounds per lineal foot. Okay. As you can see over here, here's the available sizes. The standards are 4 inches in a wide flange, a 4-inch depth, and then 120 or 100, I'm sorry, 144-inch depth, which is almost 4 feet, right? 4 inches short of 4 feet. You can see American Standard beam is designated by an S, so it's got a narrower flange. Once again, its depth, its nominal depth. Now notice that it's nominal depth, and of course we know from wood that nominal means that that's the depth it was formed at. Of course, when it cools, it shrinks, and so the actual depth may be different. So you need to go to a table if you need to know exactly what the actual depth of it is. And then the weight per lineal foot, right? So the standard sizes are from 3 inches to 24 inches. And of course, this is all set up by the manual steel construction established by the American Institute of Steel Construction. A channel often has an MC here, designating that as a channel, because there's American Standard channel too, okay? And that's just a C. And then, once again, the depth, and then the weight per lineal foot. And these are the ranges that are standard. Of course, you can always have something custom made, but as in any case, a custom costs more. And in the case of steel, costs a lot more. And then American Standard channel is, once again, expressed by its depth and its weight per lineal. You'll notice that they're about the same depths. They're more, you can go up to 18 inches with a channel, just a standard channel. Structural T, once again, WTs are split from a wide flange shapes. See the WF beam size is listed above and divide by 2 for available W2 depths. So basically, to get wide flange or a WT T, a structural T, what they do is they just cut that wide flange beam in half. Okay, so it's 1/2 of whatever the depth is, and then of course the weight. So that's how a structural T is created. And then angles, of course, L4, if it's an equal angle, each leg, then it'll say 4 and 4 here. If it's a different length, then it'll say one leg is 4, one leg is 3, and then the thickness of the angle, not the weight. So this is the thickness of the steel. And you can see here the ranges. The legs can range from 2 inches to 8 inches, and 1/8 inch in thickness up to 1 1/8 inch, which is pretty thick if you think about it. These last two here, these are actually cold rolled, and we'll talk more about them when we go into cold rolled steel, but it's called a HSS, square, rectangular, or elliptical, and then a HSS round. And like I said, we'll go into that when we go into cold rolled steel. Here is a couple of pages out of the American Institute of Steel Construction Manual. And once again, you can see all the ranges of different materials. Just, note uh, that, the area of the steel is here. That's the area of the cross section of the steel. The depth in inches. So if you're interested in what the depth is, okay, here's the actual depth for that W12 336. And then you'll see here the webbing. This is the thickness of the webbing. And to tell you the truth, I don't remember what this is right here. But it's not really important. All this information is really more important to um, your engineer, because this is what he's going to need to, the information he's going to need to make sure he's got the right size to carry the load. What's useful for you, though, is to know what the standard depth's in. So when you're designing uh, to set, you don't want to choose a depth. It may be that is visually uh, out of the range of the standard, unless you really have to. Okay, so that's the reason to look at these or be aware of the different standard depths of the beam and the widths of the flange from an aesthetic point of view. The other, or tectonic point of view, the other is that the standard forms are in families inside your BIM products such as Revit, uh, and you can be able to read and choose by kind of understanding the chart and what the different uh, signifiers, the different symbols mean. We just talked about the different shapes that are used in structure. The one thing we really haven't talked about is what is called sheet metal, which is also made either uh, by hot rolled methods or cold rolled methods. But a sheet metal is the depth of it is determined by what is called a gauge, which is a system set up in 1855 by a man named Sharp, at least the American wire gauge. There is another standard that was created later called the standard wire gauge, which is the one that's primarily used today. And the thing you need to know about this is that a gauge, you'll notice over here, here's the table of, this is the standard wire gauge table here, okay? And you'll notice the inches, in other words, a gauge, something that's 3 gauge, whether it's the diameter of a wire or the thickness of a piece of sheet metal, is, if it's gauge 3, then it's 0.2391 inches, or this is the number of millimeters, right? And this is the pounds per square foot, and this is the kilograms per square foot of area. Okay, so if you get a number 3 gauge metal, its actual depth is determined right here. Okay, this is a gauge tool, which allows you to check the gauge of a wire or a plate. The circular part, of course, is to test the wire. You run the wire through here, and that will tell you what gauge the wire is. And of course, the slot here is to gauge sheet metal. In other words, you can slide it over sheet metal. And you'll notice the gauges run from about a gauge 3. There's actually, you can go down as in standard wire gauge, you can go down to 0, what is called 0, and then all the way up to 30. Okay, in American wire gauge, I was wrong. This is the American wire gauge. Okay, so what I want you to notice, one of the things I want you to notice is that, and it's counterintuitive, but the smaller the gauge, the wider, okay, the material, okay, or the thicker the material. So if you go to a higher gauge, then the wire gets smaller or the sheet metal gets thinner. Okay. Most sheet metal roofs are in this 26 gauge or 26 gauge. Okay. Uh, so that's something to be aware of. So if somebody says, oh, we want to, this is 30 gauge versus maybe you asked for 26 gauge and they say, no, we're going to give you 29 gauge. Okay. Then that means they're giving you a thinner material. Okay. If you wanted 26 gauge and they say, okay, but all we've got is 22 gauge, you know, then that's uh, it's a lower number, but it's a thicker material. Okay. In sheet metal, there's also ferrous and non-ferrous uh, differences. Ferrous is the more ferrous there is. This is iron. This is what makes it magnetic. Aluminum, for instance, can be sheet metal can be made out of aluminum, which is a non-ferrous material. Okay. Steel cold formed. There are three basically cold formed kind of structural steel that we utilize in the industry, and that is curved structural shapes, as you can see making here, hollow structural sections, and light gauge steel. Now, curved structural steel, okay, curved beams that you may see uh, in the next slide, you can see we can curve them to make structures such as this is one of Frank Gehry's building. This is Bilbao. You'll notice though a lot of the members are straight, okay, not curved, but there are a few like this girder right here which actually are curved. So that he's used a minimal amount of structural. His buildings are built a lot like uh, the Eiffel Tower or more closely to the structural frame that holds up the um, Statue of Liberty. But you can notice then what they do is they run it through a series of rollers. Then they have to run it through there and change the degree a little bit every time. And it's done cold. The metal is not hot. It hasn't been heated up. It's just, you know, rolled out curved through these rollers that are adjusted to give you the curvature that they want. The other structural element is what is called hollow structural steel, and you'll see this is called hollow structural steel. It's commonly used. This is Arenzio Piano, it's Kansai International Airport, and the trusses are all made out of this hollow structural steel. And basically, they take a plate of material, and through a series of rollers, as you can see right here, they start to shape that steel until they roll it or cold roll it right into a shape that they want. In the case of the square HSS, it's called HSS because it's hollow structural steel, right? HSS. This is gotten by folding, running it through rollers that slowly begin to fold. Okay, so it folds this edge up, then it starts to fold this edge up until it closes here. And when it closes here, that that closure is then sealed off with a welding joint. It's welded and then of course sanded down and buffed. So it may have a really nice finish that can then just be painted. You can see this is also the same airport by Renzo Piano, and you can see all this is hollow structural steel or HSS. A circular is attained, or square is obtained by making a different, once again, a different shaping. And of course, the shaping becomes more and more extreme as we make it into a square or whether we make it into a round. There's your two examples there. The third cold rolled steel that we utilize in buildings is called light gauge steel. Y'all are probably familiar with this as metal studs. It's often called metal studs, but it's technically called light gauge steel. Um, and this is called light gauge steel framing. We're going to cover in the next lecture the fundamentals of light gauge steel framing. But you can see it's once again, it's folded into not quite so complicated a shapes as say our hollow structural steel and not near as thick. Okay, notice the thickness on this versus this is very thin, right? That's the reason it's called light gauge, meaning a very small gauge, right? I guess you could have called it small gauge steel, uh, or actually it would be large gauge steel, right? Because larger gauges are smaller, and I guess that's the reason they call it light gauge. But anyway, you can see here are the typical shapes, and we'll go into that when we get into light gauge steel framing. Okay, so that's in a synopsis of kind of steel and the ways it comes to us and kind of what it's made out of and how we make it.